The images keep coming, and with each new frame, the comfort of conventional explanations grows thinner. Space agencies promised clarity. Amateur astronomers delivered detail. Yet every sharp photograph, every spectrum, every measurement of 3I, Atlas, pushes the boundaries of what natural comet physics should allow. The jets stay straight when they should spiral. The composition defies solar system norms. The timing of its arrival threads through planetary positions with unsettling precision. This is not about wild speculation or unfounded claims. This is about data that refuses to fit, observations that challenge the models, and a growing stack of anomalies that point toward possibilities no one wanted to consider. What follows is not theory. It is evidence, measured and recorded, that something about this visitor does not add up. The geometry problem no model can solve. Standard comet physics operates on principles tested across thousands of observations spanning decades of systematic study. When a nucleus spins, material ejected from its surface should trace curved paths through space, following trajectories determined by the combination of outward gas, velocity, and rotational motion. The faster the rotation, the more pronounced the spiral becomes. For 3I, Atlas, with its confirmed rotation period of 16.16 hours and measured outflow velocities of approximately 400 meters per second, the mathematics are unforgiving and leave no room for ambiguity. Jets extending over 1 million kilometers should display obvious curvature, blurred and smeared by the nucleus, completing dozens of rotations during the material's transit time from surface to observation point. Yet the observations from multiple independent observatories show features that remain linear across their entire observable length, defying every prediction that conventional comet physics provides. The Paranal Observatory images, captured on dates throughout the post-perihelion period, revealed jets maintaining razor-straight geometry for distances exceeding 1 million kilometers. This is not a marginal deviation that might be explained by better calibration or refined atmospheric correction. This represents a fundamental conflict between what theory demands and what telescopes record. Teams at multiple observatories attempted to reconcile this geometric impossibility with variations on traditional models, exploring every avenue that might preserve natural explanations. Perhaps the jets originated from polar vents, regions near the rotation axis, where rotational smearing would be minimized to negligible levels. Detailed analysis of the jet orientations relative to the measured rotation axis ruled this out decisively, showing emission from equatorial or mid-latitude regions where rotational effects should be maximized. Perhaps the outflow velocities were far higher than spectroscopic measurements indicated, reducing transit time dramatically and limiting spiral formation to scales below instrumental resolution. Independent spectroscopic data from multiple facilities confirmed typical cometary speeds, offering no escape through this route and closing off this potential explanation. Perhaps the rotation period measurements themselves were incorrect, the product of systematic errors in photometric analysis or misidentification of the true periodicity. Independent photometric campaigns conducted from different hemispheres using different telescope systems and analysis pipelines converged on the same rotation period value to within hundredths of an hour. The measurement uncertainty is simply too small to explain away the geometric anomaly. The rotation rate is known with confidence that eliminates this as a viable source of the discrepancy. The laboratory experiments designed to test these scenarios told the same unambiguous story across multiple independent facilities. Researchers at the Southwest Research Institute spun ice mixtures in vacuum chambers under conditions that matched the comet's physical parameters as closely as current technology allows. Every single attempt produced jets that curved, fanned, or dispersed according to the expected physics. None maintained the razor-straight geometry observed in the astronomical data, despite systematic variations in experimental parameters. The Max Planck Institute adjusted rotation rates across a wide range of values, modified outflow patterns, and explored different surface compositions. JPL teams modelled shadowed craters with complex topography and varied thermal gradients. The European Space Agency facilities tested aggregate materials with different structural properties. The results were consistent across all facilities, all methodologies, and all parameter spaces explored. Under rotation, matching the observed period, sustained straight jets spanning millions of kilometers are physically implausible without some mechanism actively maintaining their alignment against the natural tendency towards spiral formation. This is not a subtle discrepancy that might be explained by better calibration, more sophisticated models, or previously overlooked secondary effects. The geometry problem represents a fundamental conflict between observation and theory at the most basic level. The physics governing rotating bodies and gas dynamics are among the most thoroughly understood in planetary science, tested across countless applications from atmospheric dynamics to industrial processes. If those principles hold universally, the observed jet structure cannot exist in nature. If the observations are accurate and free from systematic error, something beyond standard comet physics must be operating to maintain jet alignment. The possibility that both statements are true simultaneously, that the data is reliable, and the fundamental physics sound, forces consideration of mechanisms that lie outside the traditional framework of cometary science. This is where the conversation becomes uncomfortable for mainstream astronomy, where established theory meets the boundaries of what natural processes have been demonstrated to explain. The geometry problem alone does not prove any specific alternative hypothesis, but it does prove conclusively that conventional comet models fail to account for the most prominent visual feature of 3I, Atlas, the feature that dominates every high-quality image and defines the object's appearance in ways that cannot be ignored or dismissed. Composition beyond solar system chemistry. Every comet previously studied in detail, whether originating from the Oort cloud, the Kuiper belt, or the scattered disk population, shares a chemical signature fundamentally consistent with solar system formation processes and the composition of the primordial nebula. Water ice dominates the volatile inventory, typically comprising 50 to 80% of the total mass. Carbon dioxide, carbon monoxide, methane, and ammonia appear in predictable ratios that reflect the temperature and pressure conditions in different regions of the protoplanetary disk. Trace metals appear in abundances that closely match the solar photosphere composition, confirming that comets represent relatively unprocessed samples of the material from which planets formed. This consistency across dozens of well-studied comets establishes a baseline for what natural solar system objects should look like chemically. 3I, Atlas, breaks this pattern completely and decisively across multiple independent measurements. Spectroscopic analysis from the James Webb Space Telescope, the Very Large Telescope, and multiple ground-based facilities reveals a composition that stands apart from every known natural body in our cosmic neighborhood. The deviations are not subtle variations within the expected range. They represent order of magnitude departures from established norms that cannot be explained by standard astrophysical processes or unusual formation conditions within known stellar environments. The nickel-to-iron ratio emerged as the first major red flag during the initial spectroscopic observations and has been confirmed repeatedly through subsequent measurements. In typical solar system material, From meteorites to planetary cores to cometary dust, iron dominates over nickel by factors ranging from 10 to 50. This reflects the relative abundance of these elements produced by stellar nucleosynthesis processes in the supernova explosions that created the heavy elements. Iron 5-6 is among the most stable nuclei and forms as the end point of fusion reactions in massive stars. Nickel, while chemically similar, is produced in smaller quantities by the same processes. The solar ratio of iron to nickel reflects billions of years of galactic chemical evolution and stellar processing. The James Webb Space Telescope detected nickel emission lines with intensities that exceed standard model predictions by factors of 100 to 300. Depending on the specific transitions examined and the assumed excitation conditions, the Very Large Telescope's high-resolution spectrographs confirmed these measurements independently, using different instrumental configurations and analysis techniques. Cross-calibration between facilities eliminated systematic errors as an explanation. The nickel-to-iron ratio in the 3I Atlas coma is inverted compared to solar system norms, with nickel dominating by factors of 2 to 5, depending on the specific measurement technique and ionization state examined. Statistical analysis quantifies the extreme nature of this anomaly with precision. Based on the current census of cometary compositions, spanning hundreds of objects observed spectroscopically, the probability of finding such an extreme nickel-to-iron ratio by random chance falls below 1%. This places 3I Atlas in the outermost tail of the distribution, far beyond what random variation or measurement uncertainty could produce. The measurement represents a genuine outlier that demands explanation through physical processes, not statistical fluctuation. Attempts to explain this through unusual formation conditions in another stellar system face immediate and severe challenges from basic nuclear physics. While different stars produce different elemental abundances depending on their mass, metallicity, and evolutionary state, the nickel-iron ratio is constrained by fundamental properties of nuclear binding energy and stellar nucleosynthesis pathways. No known stellar evolution pathway or supernova mechanism produces the dramatic nickel enrichment observed in the comet's emissions without simultaneously producing other elemental anomalies that are not detected. The observed composition pattern does not match predictions for material formed around low metallicity stars, high mass stars, or stars with unusual composition. It does not match ejecta from any known supernova type. It does not match predictions for material processed through stellar winds or planetary nebulae. The water deficiency compounds the chemical puzzle in ways that challenge fundamental assumptions about comet formation. Comets are often described as dirty snowballs, a characterization based on decades of observations showing water ice comprising 50 to 80% of nuclear mass for typical objects. The snow component dominates, with rock and dust acting as minor contaminants embedded in an ice matrix. 3I Atlas shows water vapor at just 4% of the coma's composition by mass, as measured through multiple independent techniques, including infrared spectroscopy and ultraviolet observations of hydrogen emission. This is not simply low by cometary standards. It represents a value orders of magnitude below the threshold that defines cometary behavior and distinguishes comets from asteroids in standard classification schemes. Without substantial water ice providing both the volatile inventory and the structural binding agent, the mechanism driving the observed outgassing becomes fundamentally unclear. Carbon monoxide and carbon dioxide can sublimate at solar distances and produce gas jets through the same physical processes that drive water sublimation. However, the observed activity levels, mass loss rates, and jet velocities exceed what these volatiles alone should generate by substantial margins. The power budget does not close using known sublimation physics and measured volatile abundances. The arrival timing that defies probability. Orbital mechanics is fundamentally deterministic within its domain of applicability. Given a starting position, velocity, and the gravitational field through which an object moves, the future path through space can be calculated with extraordinary precision, limited only by measurement, accuracy, and computational resources. When astronomers work backward from current observations to trace where 3I Atlas came from and forward to predict where it goes, the results raise immediate questions that resist comfortable answers. The comet's trajectory brought it through the inner solar system along a path that maximized concealment from Earth-based detection while threading past multiple planets with remarkable precision that borders on the statistically implausible. The timing of perihelion, the point of closest approach to the Sun, where solar heating peaks and cometary activity maximizes, came just 8 days after solar conjunction from Earth's perspective. This geometric alignment placed the comet directly behind the Sun as viewed from Earth for a period of several weeks during its most active phase, when outgassing rates peaked and visual features developed most dramatically. Ground-based observations were completely impossible during this critical period due to the proximity to the solar disk. Even space-based observatories faced severe pointing restrictions designed to protect sensitive instruments from direct or scattered solar radiation that could damage detectors or saturate sensors beyond recovery. The window of maximum observability from both scientific and public interest perspectives coincided almost perfectly with the window of minimum detectability from both ground and space-based platforms. Calculating the probability of this alignment requires examining the full parameter space of possible approach trajectories for interstellar objects. A hyperbolic orbit can arrive from any direction on the celestial sphere and reach perihelion at any point along its path around the Sunday. The fraction of this parameter space that produces solar conjunction within days of perihelion is geometrically constrained. Detailed Monte Carlo analysis, incorporating realistic observational constraints, shows that less than 3% of randomly generated hyperbolic orbits would produce such favourable concealment conditions. This is not an extraordinarily unlikely coincidence by itself. 3% of events happen regularly by chance. However, this probability must be combined with other geometric and timing factors to assess the full coincidence stack. The planetary encounters add substantial layers to the probability calculation and the growing puzzle of geometric alignments. 3I Atlas passed within several million kilometers of Mars during its inbound trajectory, approaching distances that made the comet potentially observable from Mars orbit by spacecraft like the Mars Reconnaissance Orbiter. However, the encounter geometry occurred when Mars was positioned on the far side of the Sun from Earth, making real-time coordination of observations challenging and data transmission subject to delays and interruptions during solar conjunction periods. Venus received a similarly close approach at a distance that would have made the comet easily visible from Venus orbit if observing spacecraft were appropriately positioned. The encounter occurred when Venus appeared in gibbous phase from Earth, its bright disk overwhelming faint objects in the same field of view and making detection of a comet approaching from similar sky positions extraordinarily difficult for ground-based surveys. Jupiter's orbital position during the comet's traverse of the outer solar system placed 3I Atlas against the dense star fields of the galactic plane for extended periods, where automated survey systems struggled to distinguish moving objects from the overwhelming background of stars and suffer reduced detection efficiency. Each planetary encounter occurred when that planet's position minimized gravitational perturbation of the comet's path, while simultaneously maximizing the difficulty of detection from Earth-based platforms. Mars was opposite the Sun, Venus was in an unfavorable phase. Jupiter provided a background that challenged detection algorithms. Multiple orbital dynamicists working independently have run extensive Monte Carlo simulations, generating millions of random interstellar trajectories with parameters drawn from plausible distributions based on galactic kinematics and stellar ejection mechanisms. The fraction of simulated trajectories that matches the observed path characteristics, timing of perihelion relative to conjunction, and the specific planetary encounter geometries observed for 3I, Atlas, falls well below 1 in 10,000. This quantifies the degree of coincidence required for a random trajectory, determined solely by the object's ejection velocity from its origin system and the gravitational fields encountered during its interstellar journey, to display these features simultaneously. Natural interstellar objects follow paths determined entirely by these initial conditions and gravitational perturbations. The odds of those random factors aligning to produce maximum concealment from the solar system's primary observing platform strain credibility when considered in totality. Magnetic fields, where none should exist. Comets are fundamentally non-magnetic objects, based on all previous direct measurements and theoretical understanding of their composition and structure. The ices that comprise the dominant mass fraction contain no ferromagnetic materials. The dust and rocky components that provide structural support consist primarily of silicates, carbonaceous materials, and metal grains that individually may have magnetic properties, but collectively cancel in randomly oriented aggregates. Previous spacecraft missions to cometary nuclei, including detailed magnetic field surveys conducted by the Rosetta spacecraft during its extended Comet Churyumov-Gerasimenko encounter, confirmed the absence of intrinsic magnetic fields at levels well below natural remnant magnetization strengths observed in meteorites and lunar samples. Any magnetic fields detected in the vicinity of comets arise from interactions between the solar wind and the ionized coma, not from the nucleus itself. The solar wind carries a magnetic field frozen into the outflowing plasma. When this magnetized plasma encounters the comet's neutral coma, ionization creates electrically conducting regions that interact with the carried field, draping it around the obstacle and creating characteristic structures like magnetic field line pile-up regions and tail disconnection boundaries. These interaction-driven fields are well understood theoretically and reproduced in laboratory plasma experiments and numerical simulations. They represent responses to external driving rather than intrinsic properties of the cometary body. This established understanding makes the magnetic field measurements around 3I Atlas particularly difficult to explain within conventional frameworks, and particularly significant as potential indicators of anomalous properties. Plasma wave instruments aboard spacecraft operating in the inner solar system during the comet's perihelion passage detected structured magnetic field variations that correlate with the comet's position in ways that external solar wind interactions alone cannot explain. These are not the diffuse, irregular field structures associated with solar wind draping and ionospheric interactions that vary with solar wind conditions and show no intrinsic periodicity tied to the comet itself. The measurements show organized patterns with periodicities matching the comet's rotation period of 16.16 hours to within measurement uncertainty. This temporal correlation suggests a source fixed to the rotating nucleus rather than a product of external plasma processes that would show periodicities related to solar wind variations or orbital motion. The field strength, while modest on absolute scales, exceeds theoretical predictions for magnetically inactive bodies by factors of hundreds based on standard models of ionospheric conductivity and induced field generation. Attempts to attribute these fields to enhanced induced magnetization through unusually strong ionospheric currents face immediate quantitative obstacles. The comet's composition, particularly the low water content, confirmed by multiple spectroscopic measurements, and the unusual metal ratios that deviate from solar system norms, does not support the electrical conductivity required for strong induced fields through standard ionospheric dynamo mechanisms. Even with generous assumptions about subsurface ice layers, dissolved salts enhancing conductivity and optimal geometry for current systems, the calculated magnetic field properties fall short of observations by order of magnitude factors. Natural explanations invoke increasingly complex scenarios to bridge the gap between theory and measurement. Perhaps metallic dust grains become aligned by some process and produce bulk magnetic properties through collective effects. Laboratory experiments show that radiation pressure, electrostatic forces, and gas drag can produce grain alignment under specific conditions. However, maintaining coherent alignment across the spatial scales required while the grains move through the expanding coma requires forces that exceed what these mechanisms provide. Perhaps transient plasma currents create temporary field structures that happen to be sampled during measurement periods. Statistical analysis of measurement timing argues against this coincidence explanation. The magnetic field measurements come from multiple independent platforms using different detection techniques and observing from different vantage points. Maven's magnetometer recorded anomalous readings exceeding background noise levels by factors sufficient for confident detection during the comet's closest approach to Mars orbit. Solar wind monitoring spacecraft positioned at the first Lagrange point detected structured disturbances in the interplanetary field downstream of the comet's orbital position, at times consistent with field structures attached to the plane, moving nucleus. Ground-based radio observations using polarimetry techniques picked up signatures consistent with organized magnetic fields in the inner coma regions where plasma density peaks. The convergence of different measurement techniques, each sensitive to different aspects of magnetic field structure and strength, all pointing toward the same basic conclusion, strengthens the case that something physically unusual is occurring. This is not an instrumental artifact from a single platform or a misinterpretation of data from one technique. The detection is robust across multiple independent confirmations. The radiation pressure paradox. When sunlight strikes dust particles ejected from a comet's surface, radiation pressure from absorbed and scattered photons pushes them away from the sun along radial trajectories. This force, though tiny on human scales, becomes significant for small grains over the vast distances of interplanetary space. For particles smaller than several micrometers, radiation pressure can exceed solar gravity, causing them to accelerate outward faster than gravitationally bound orbits would predict. This process shapes the dust tail into its characteristic curved streamer, pointing generally away from the sun but curved backward along the orbital path due to the finite time required for particles to accelerate to their terminal velocities. The morphology of dust tails provides a reliable diagnostic tool for estimating particle sizes and compositions through detailed modeling that accounts for optical properties, solar radiation spectrum, and orbital geometry. Particles of different sizes respond differently to radiation pressure, with smaller grains accelerated more strongly and larger grains remaining closer to the nucleus trajectory. The resulting size-dependent separation creates tail structures whose shapes encode information about the dust size distribution. For 3I Atlas, the radiation pressure effects observed in tail morphology do not match theoretical predictions based on spectroscopic composition measurements. suggesting either unprecedented particle properties or additional forces beyond photon momentum transfer. The observed dust tail morphology, as captured in high-resolution images from both professional observatories and amateur astronomers using advanced imaging equipment, implies particle sizes inconsistent with the spectroscopic composition determined from analysis of scattered light properties. Large grains, several micrometers across, would produce the observed tail shape and curvature, given typical cometary dust densities and standard optical properties of silicate and carbonaceous materials. The tail appears broader and less strongly curved than would result from submicron particles dominating the size distribution. Yet the spectroscopic signatures obtained from analysis of scattered sunlight and thermal emission indicate much smaller particles, submicron grains that should be swept away much more rapidly by radiation pressure and produce tails with different morphological characteristics. The wavelength dependence of scattered light intensity and polarization provides strong constraints on particle size when combined with reasonable assumptions about composition and structure. Multiple independent analyses using different spectroscopic features converge on size distributions peaked at fractions of a micrometer, inconsistent with tail morphology observations. Reconciling these conflicting measurements within natural frameworks requires either abandoning standard optical properties of cometary dust materials or introducing additional forces that modify particle trajectories in ways that mimic the effects of larger particle sizes. Detailed modelling efforts explored both avenues extensively without achieving satisfactory resolution. Perhaps the dust particles have highly unusual shapes, extreme elongations, or fractal aggregates that alter their interaction with sunlight in ways that standard spherical or irregular particle models do not capture. Extensive laboratory measurements of light scattering by particles with various morphologies constrain how much shape effects can influence optical properties. The variations are real but insufficient to explain the magnitude of the discrepancy. Perhaps the particles carry substantial electric charges due to photoelectric emission or plasma interactions, and these charges, coupled to the interplanetary magnetic field carried by the solar wind. Charged particle dynamics in magnetized plasmas differ fundamentally from neutral grain dynamics, with forces perpendicular to both field and velocity directions that can modify trajectories in complex ways. However, quantitative calculations of this mechanism face severe problems. The magnetic field strength in the inner solar system and the charge-to-mass ratios achievable through natural charging processes combine to produce forces of orders of magnitude too weak to account for the observed tail. Modifications. Even invoking maximum possible charging levels and most favourable field geometries, the calculated magnetic forces fall short by factors of 10 or more, outgassing rates that break energy conservation. Every comet approaching the Sun loses mass as solar heating drives sublimation of surface and near-surface ices. The outgassing rate depends on several factors that can be calculated from first principles or estimated from observations with reasonable confidence. The surface area receiving sunlight sets the scale for how much energy the nucleus absorbs. The composition of the ices determines the vapor pressure and sublimation rate as a function of temperature. The thermal properties of the nucleus material control how efficiently absorbed solar energy reaches subsurface ice reservoirs rather than being radiated back to space. For 3I, Atlas, the observed outgassing rates derived from spectroscopic measurements of gas production exceed what the estimated surface area can produce, even under the most optimistic assumptions about composition and thermal conductivity. This represents not a marginal discrepancy that might be resolved through better parameter estimates, but a fundamental violation of energy conservation principles if the standard size estimates and heating model are both correct. Photometric observations combined with thermal modeling constrain the nucleus size through multiple independent techniques. Analysis of light curves, the periodic variations in brightness as the irregular nucleus rotates, provides information about size, shape, and surface reflectivity. Thermal infrared observations measure the heat radiated by the nucleus, which combined with assumptions about thermal inertia constrains both size and surface temperature. Multiple analysis methods, from sophisticated shape models that match rotational light curve details to simpler estimates based on peak brightness and assumed albedo, converge on a maximum diameter between 3 and 5 kilometers for the 3I Atlas nucleus. This size constraint sets an upper limit on the surface area available for active outgassing. Even assuming the entire surface remains active with no inactive regions, which never occurs in real comets, the geometric constraint is absolute. A 5-kilometer diameter sphere has a surface area of approximately 79 square kilometers. Only half receives direct sunlight at any given time, further reducing the active area. Given typical cometary albedos in the range of 4 to 6%, the absorbed solar power at the perihelion distance can be calculated directly from the solar constant and geometric factors. This sets the total energy budget available to drive sublimation. For water ice, the most efficient cometary volatile in terms of sublimation energy, the enthalpy of sublimation determines how much ice can be vaporized per unit of absorbed energy. Taking the measured solar power input and dividing by the sublimation enthalpy yields the maximum possible mass loss rate if all absorbed energy drives ice sublimation with perfect efficiency. These calculations account for the most favorable conditions, assuming maximum surface activity with no inactive areas, using thermal models optimized for high outgassing efficiency, and selecting the most volatile cometary ices with lowest sublimation barriers. The observed gas production rates, measured through analysis of spectroscopic emission lines and ultraviolet observations of extended hydrogen coma, exceed these theoretical maxima by factors of 3 to 5 depending on the specific measurement technique and assumed excitation conditions. This is not a marginal discrepancy that better modelling might resolve through more sophisticated treatment of surface processes or thermal physics. The energy required to drive the observed outgassing levels simply is not available from solar heating alone, given the size constraints imposed by independent photometric observations. Attempts to explain this violation of energy balance through internal heat sources face immediate and insurmountable quantitative obstacles. Radioactive decay of long-lived isotopes like potassium-40, thorium-232, and uranium-238 provides internal heating in large planetary bodies and contributes to geological activity on objects like Jupiter's moon Io. However, the power output from radioactive decay scales with mass and depends on isotopic abundances. For a body with a few kilometers diameter, assuming even generous abundances of radioactive elements at levels found in undifferentiated chondrite meteorites, the total radiogenic heating falls short of requirements by factors of thousands. Chemical reactions between reactive species could in principle release energy that supplements solar heating. Laboratory studies of cometary ice analogues show that certain chemical reactions, particularly those involving peroxide compounds or trapped radicals, can release substantial energy when triggered. However, the total energy stored in chemically reactive bonds represents a finite reservoir that depletes as reactions proceed. To sustain the observed outgassing for the weeks-long period during which measurements were obtained would require chemical energy densities exceeding those of high explosives. No plausible cometary composition provides such energy storage capacity. Residual heat from the object's formation represents another potential internal energy source. Gravitational collapse during accretion converts potential energy to heat, and collisions during late-stage assembly add kinetic energy. For large planetary bodies, this primordial heat dominates the thermal budget for billions of years. However, for small objects like cometary nuclei, the heat capacity is tiny and radiative cooling extremely efficient. Any formation heat would dissipate on timescales of thousands to millions of years, far too short to remain significant for an object that has travelled through interstellar space for potentially millions or billions of years since its formation. The persistent negative polarization signal. When light reflects or scatters from dust particles, the electric field oscillations that constitute electromagnetic radiation can become polarized, meaning the field oscillates preferentially in certain orientations rather than remaining randomly distributed. The degree of polarization and its sign, positive or negative relative to the scattering plane, depend sensitively on particle size, composition, shape, and the angle between incident and scattered light directions, known as the phase angle. Polarimetric observations of reflected sunlight from cometary dust provide powerful constraints on these particle properties, often revealing details not accessible through other observational techniques. Cometary dust, observed across hundreds of objects, typically produces positive polarization at most phase angles accessible from Earth-based observation geometries. The polarization degree increases with phase angle, reaching maximum values of tens of % for phase angles approaching 90 degrees. This behavior matches theoretical predictions for particle sizes comparable to or larger than visible light wavelengths composed of materials with refractive indices typical of silicates and carbonaceous compounds. Laboratory measurements of light scattering by analog materials confirm the theoretical predictions and validate the interpretation of cometary polarimetry in terms of standard dust properties. 3I Atlas shows sustained negative polarization across a wide range of viewing geometries and phase angles, a pattern that challenges every standard scattering model developed through decades of cometary polarimetry studies. Negative polarization occurs when the electric field perpendicular to the scattering plane dominates over the parallel component, opposite to the usual situation. Theoretical models predict this can occur for either extremely small particles, much smaller than the wavelength of light, or for particles with very unusual optical properties that reverse the normal scattering behavior. For spherical particles, Mie scattering theory provides exact solutions for how light scatters as a function of particle size, composition characterized by complex refractive index, and scattering geometry. These solutions predict narrow ranges of sizes and compositions that produce negative polarization. Matching the observed polarization signature from 3I Atlas requires either metallic particles with diameters smaller than 1/10 of a micrometer, or dielectric particles with refractive indices far outside the range known for. Natural cometary materials. Neither option fits comfortably with other observational constraints from spectroscopy and thermal measurements. Metallic particles of the required size would produce distinctive spectroscopic features through plasmon resonances and absorption edges that are not observed in the 3-ATLAS spectrum. Additionally, metals sublimate at temperatures far below what the nucleus surface experiences at perihelion distances, making it difficult to understand how metallic grains would survive to be ejected into the coma. Dielectric particles with the required extreme refractive indices would need compositions unlike any known natural minerals, with optical properties that do not match laboratory measurements of candidate materials. The persistence of the negative polarization signature over weeks of observation and across changing phase angles as the comet moved and Earth's viewing geometry evolved eliminates simple explanations based on transient viewing. Effects or isolated dust events. Standard polarization models predict that the sign of polarization should flip from negative to positive as the phase angle varies through specific critical values that depend on particle properties. The fact that 3I, Atlas, maintained negative polarization across phase angle changes of tens of degrees requires either an extraordinarily narrow and fine-tuned range of particle properties that remains stable as the coma evolves, or a fundamentally different scattering mechanism not accounted for in conventional models. Laboratory experiments attempted extensively to recreate the polarization signature using the full range of dust analogues available to planetary science. Researchers at multiple facilities tested metal particles of various compositions and size distributions, carbon grains in forms ranging from amorphous carbon to graphite, silicate particles with different mineralogies and structures, and various types of aggregates and coated particles designed to mimic complex cometary dust morphologies. The experiments spanned wavelength ranges from ultraviolet through visible to near-infrared, matching the observational datasets. None of the materials tested reproduced the observed polarization pattern across the full range of wavelengths and phase angles measured for 3I-ATLS. The closest experimental matches required particles with properties that do not occur naturally through grain formation processes observed in protoplanetary disks, molecular clouds, or stellar winds. Specifically, achieving the observed polarization behavior required precise size distributions with widths narrower than natural growth processes produce and surface structures implying processing beyond natural abrasion or radiation damage. The negative polarization remains among the most puzzling optical properties of 3I, Atlas, with no satisfactory natural explanation emerging despite intensive modelling efforts and laboratory experimental programs specifically designed to address this anomaly. Spectral absorption features from unknown materials. Spectroscopy provides the most direct and quantitatively reliable window into the composition of cometary material. By analysing how light is absorbed and emitted at different wavelengths, astronomers can identify chemical species present in cometary nuclei, comas, and tails with remarkable precision and specificity. Each molecule and atom produces characteristic spectral features at wavelengths determined by quantum mechanical energy level structures. These spectral fingerprints are as unique and identifiable as human fingerprints, allowing unambiguous identification when sufficient spectral resolution and signal strength are available. The spectrum of 3I, Atlas, obtained from multiple high-resolution spectrographs on premier facilities, includes absorption and emission features that do not match any known molecules or atomic transitions in comprehensive spectroscopic databases compiled over decades of laboratory measurements and theoretical calculations. These unidentified lines appear consistently across multiple observation sessions, separated by days to weeks, confirming they represent real features of the comet rather than transient instrumental artifacts or atmospheric contamination. The spectral features appear in data from different instruments using different optical designs and detector technologies, eliminating instrument-specific systematic errors as explanations. The strongest unidentified features appear in both the near-infrared region, where vibrational transitions of molecules typically dominate, and the ultraviolet region, where electronic transitions and atomic resonance lines are most prominent. Careful wavelength calibration using known atmospheric lines and standard spectroscopic sources confirms the central wavelengths of these features to precisions of better than 1 part in 10,000, eliminating wavelength measurement errors as the source of non-identification. The absorption depths reach tens of % relative to the adjacent continuum for the strongest features, indicating substantial column densities of the unknown absorber must be present along the line of sight through the coma. Comparison with laboratory spectra of thousands of candidate compounds failed to produce convincing matches for these features. Initial searches focused on simple molecules known to exist in cometary environments including various hydrocarbons, nitrogen-bearing species, oxygen compounds, and sulfur-containing molecules. None matched. Expanded searches included more complex organic compounds, particularly those containing multiple functional groups or ring structures that might form in interstellar or cometary ices through radiation processing. Still no matches emerged. Exotic molecules proposed in various astrochemical contexts, including carbon chains, silicon-bearing species, and molecules containing unusual bonding configurations, were considered systematically. The unidentified features persisted without plausible assignments. Molecular spectroscopists calculated predicted spectroscopic properties for increasingly speculative candidate molecules using state-of-the-art quantum chemistry computational methods. These calculations can predict transition wavelengths, intensities, and spectral line profiles with accuracies approaching experimental precision for molecules containing up to dozens of atoms. The calculations explored unusual metal-bearing molecules, metastable excited electronic states, and molecular ions in various charge states. None of the calculated spectra matched the observed features within the combined uncertainties of calculation and measurement. The mystery deepened as additional high-resolution spectra obtained during subsequent observation runs confirmed and refined the initial measurements. The unidentified features appeared with consistent wavelengths and relative intensities across observations separated by weeks, ruling out transient phenomena or rapidly evolving chemical processes. Their presence in both emission mode when viewing the coma against dark sky and absorption mode when the comet passed in front of background stars demonstrates these features arise from real material in the comet rather than instrumental or atmospheric effects. Something in the comet's composition lies demonstrably outside the known catalogue of natural chemical species observed in any solar system object, interstellar cloud, or stellar atmosphere. The spectral features are incompatible with all molecules in comprehensive databases spanning hundreds of thousands of laboratory-measured spectra. This is not a situation where several candidate identifications remain ambiguous. This is a situation where 0 plausible identifications exist, despite exhaustive searches. The unidentified absorption features represent one of the most concrete and difficult to dismiss anomalies in the 3I Atlas dataset, pointing toward material composition that current chemistry and spectroscopy cannot explain. Thermal emission anomalies. Infrared observations measure the heat radiated by cometary nuclei and their surrounding dust comas, providing constraints on temperatures, thermal inertia, and energy balance that complement visible light observations. The thermal emission spectrum and its spatial distribution encode information about how efficiently absorbed solar energy redistributes through thermal conduction, how rapidly surfaces respond to changing illumination, and whether internal heat sources contribute to the observed temperatures. For 3I Atlas, the thermal emission pattern does not follow expected behaviors for a rotating body in sunlight under standard heat transfer physics. Standard thermal models for rotating airless bodies account for multiple physical processes that govern surface temperatures. Solar radiation absorbed during daytime heats the surface according to the local solar zenith angle. Some absorbed energy radiates back to space immediately as thermal infrared emission. Some conduct into the subsurface, stored in the heat capacity of near-surface material. As the surface rotates into darkness, this stored heat conducts back out and radiates to space, maintaining elevated nighttime temperatures above what instantaneous radiative equilibrium would produce. The balance between daytime absorption, thermal emission, and subsurface conduction determines the temperature distribution across the rotating surface. These models successfully reproduce observations of solar system comets, asteroids, and planetary satellites across wide ranges of sizes, compositions, rotation rates, and orbital distances. The models have been validated through spacecraft missions that provided both thermal imaging and ground truth measurements of surface properties. Applied to 3I, Atlas, using its measured rotation period, estimated size, and known orbital position, these standard thermal models predict strong temperature contrasts between illuminated and shadowed hemispheres, and characteristic phase lags between maximum solar heating and maximum infrared emission as different parts of the surface rotate through the diurnal cycle. The actual thermal infrared measurements show temperature distributions much more uniform than models predict, and phase lags that differ significantly from expectations based on standard thermal inertia values for cometary material. The temperature difference between the subsolar point, where solar heating peaks, and the terminators, where illumination angles graze the surface, measures only 20 to 30% of the predicted contrast. Infrared images, taken at different rotational phases, show thermal emission patterns that remain remarkably stable rather than rotating with the expected period or showing the anticipated shifts as hot regions move around the nucleus. The most straightforward explanation for reduced temperature contrasts would involve unusually high thermal conductivity in the nucleus material, allowing heat to flow rapidly from illuminated to shadowed regions and homogenizing temperatures across the surface. However, calculating the required thermal conductivity to match observations yields values that exceed those of solid water ice by factors approaching 1,000. Even metallic materials like iron or aluminum do not conduct heat efficiently enough to explain the uniform temperatures at the measured rotation rate and nucleus size. Natural porous materials, like those confirmed to comprise known cometary nuclei through measurements by the Rosetta and Deep Impact missions, have thermal conductivities orders of magnitude too low to produce the observed thermal homogenization. Alternative models explored invoke subsurface heat sources distributed through the nucleus volume that supplement solar heating and reduce relative temperature contrasts. Radioactive decay, the heat source powering Earth's interior and driving tectonics on larger bodies, provides far too little power for objects of cometary size and composition. Even assuming highly enriched concentrations of uranium and thorium beyond any levels observed in meteorites, the radiogenic heating rate per unit mass remains negligible compared to solar heating at perihelion distances. Chemical reactions between reactive species stored in the ice matrix could release heat, but sustaining the required power output would consume the available reactants in timescales much shorter than the observation period spans. The thermal emission phase lag anomaly adds another puzzle independent of the temperature uniformity issue. When a rotating surface element moves from shadow into sunlight, its temperature does not respond instantly. Heating the surface material and near subsurface layers takes time determined by thermal inertia and heat capacity. Similarly, when rotating into shadow, cooling proceeds gradually rather than instantaneously. These thermal response times create phase lags, shifts between the time of maximum solar illumination and the time of maximum temperature and infrared emission. Standard thermal models predict phase lags of several hours for typical cometary material properties and the measured rotation period. The observed infrared emission from 3I Atlas peaks with much shorter phase lags, or in some analyses with phase leads, where peak emission occurs before peak illumination, physically impossible under passive solar heating alone. The missing fragmentation events. Comets are structurally fragile objects, held together primarily by weak ice bonds and modest self-gravity, insufficient to compress material to high density. The history of cometary observations is filled with examples of fragmentation events where nuclei split into multiple pieces or disintegrate entirely into expanding debris clouds. Famous historical examples include Comet Shoemaker-Levy 9, which fragmented into more than 20 distinct pieces during a close approach to Jupiter before the fragments crashed into the planet. Comet Lineaire disintegrated completely during its approach to the Sun, leaving only a diffuse debris cloud. Comet Elenin broke apart and essentially dissolved before reaching perihelion. Statistical studies of long-period comets making their first passage through the inner solar system show that substantial fractions, estimated at 20 to 40% depending on perihelion distance, experience observable fragmentation events. The physical processes driving fragmentation include thermal stress from rapid heating as the nucleus approaches the Sun, tidal stress during close approaches to massive bodies, and internal pressure buildup from gas trapped in subsurface ice that explosively fractures the nucleus structure. For comets approaching within Venus orbit distance from the Sun, as 3I Atlas did, fragmentation becomes increasingly likely as thermal stresses maximize. The perihelion distance of 3I Atlas brought it to within approximately 0.72 astronomical units from the Sun, well inside the orbit of Venus, and into regions where solar heating reaches levels capable of vaporizing surface ices at rates that create substantial internal pressure if gas cannot escape freely. The thermal environment at this distance has proven sufficient to disrupt previous comets with similar approach parameters. Additionally, 3I Atlas approached at high velocity on its hyperbolic trajectory, experiencing more rapid temperature changes than objects on elliptical orbits that spend longer times at intermediate solar distances. Rapid thermal changes increase mechanical stress through differential expansion of material with varying ice and rock content. Every factor identified through previous studies as promoting cometary fragmentation was present and amplified for 3I Atlas. Yet, comprehensive photometric monitoring throughout the perihelion passage shows no evidence of fragmentation events. The light curves, detailed brightness measurements, obtained at regular intervals through the critical weeks bracketing perihelion, display stable periodic variations consistent with a single rotating nucleus. Fragmentation produces characteristic signatures in light curves, including sudden brightness increases as fresh ice becomes exposed, or as the total cross-section increases when fragments separate, followed by more complex variations as multiple bodies tumble independently. None of these signatures appear in the 3I Atlas photometric data. The variations remain smooth and periodic, matching patterns expected from a coherent rotating body without evidence of structural changes. High-resolution imaging conducted immediately after perihelion, when the comet emerged from solar conjunction and became accessible to major observatory facilities, revealed a single compact nucleus surrounded by its characteristic coma structure. No nearby fragments appeared in any images, despite detection limits sensitive enough to reveal pieces as small as tens of meters across, if separated by more than a few nucleus diameters. No debris trails appeared extending along the orbit, in directions that would indicate recently separated material following slightly different trajectories. The coma maintained its structure and jet patterns without the dramatic expansions or morphology changes that accompany breakup events, as internal structure disrupts and massive amounts of fresh material suddenly sublimate. All available evidence from multiple independent observation techniques converges on the conclusion that the 3I Atlas nucleus remained completely intact throughout perihelion passage, without experiencing any of the fragmentation, splitting, or disruption events that commonly affect comets in similar dynamical and thermal environments. This survival requires structural strength and internal cohesion exceeding what natural ice rock aggregates typically provide. Structural modelling explored whether favourable combinations of shape, rotation, state, and internal structure might explain the observed resilience within natural bounds. Calculations of tensile strength, the force per unit area required to mechanically separate material, show that natural aggregates of ice and dust particles, bound by weak sintering and van der Waals forces, provide strengths typically measured in thousands of pascals. The stresses imposed by thermal expansion, outgassing pressure, and tidal effects during perihelion passage of 3I Atlas reach levels orders of magnitude higher. Natural material should have failed structurally, resulting in at minimum partial fragmentation or surface disruption, if not complete disintegration. Even allowing for optimistic assumptions about unusual strength through prior sintering, compaction from long-duration exposure to cosmic rays, or structural reinforcement through rocky inclusions embedded in the ice matrix, the predicted survival probability falls well below 50% based on comparison with the observed fragmentation rates for comets in similar thermal environments. The fact that 3I Atlas not only survived perihelion intact, but showed absolutely no signs of stress, degradation, or partial disruption implies material properties and structural cohesion that significantly exceed natural bounds established through studies of meteorites, cometary samples, and theoretical models of aggregate strength. The anomalous acceleration profile, tracking the precise position of any solar system object over extended time periods, allows determination of its orbit with accuracy that improves as the observation baseline lengthens. For comets, comparing observed positions with predictions from purely gravitational orbital models reveals discrepancies caused by non-gravitational forces, primarily the rocket-like thrust from asymmetric outgassing as material sublimates and escapes from the nucleus. These non-gravitational accelerations are extremely well characterized for solar system comets, following predictable patterns based on the comet's distance from the Sun, its rotation state, and the distribution of active regions across the surface. Standard models of non-gravitational forces parameterize the acceleration in terms of radial, transverse, and normal components relative to the orbital plane. The radial component points directly away from or toward the Sunday. The transverse component lies in the orbital plane perpendicular to the radius vector. The normal component points perpendicular to the orbital plane. For typical comets, the radial component dominates, arising from outgassing thrust, pointing approximately away from the Sun as heated surfaces sublimate. Smaller transverse components arise when active regions are not positioned symmetrically, or when rotation causes time lags between peak heating and peak outgassing. Normal components are typically smallest, appearing only when significant asymmetries exist between the northern and southern hemispheres, or when the rotation axis has substantial obliquity. Astrometric measurements of 3I Atlas, obtained from multiple observatories, provide position data with uncertainties less than 1/10 of an arcsecond for the best observations. Converting these angular positions to physical positions in space requires accurate knowledge of Earth's position and the observing geometry, both well established through planetary ephemerides with precision exceeding the measurement uncertainties. Comparing these observed positions with predictions from gravitational orbits that account for perturbations from all major planets and even the more massive asteroids reveals systematic discrepancies that grow with time, the signature of continuous non-gravitational acceleration. The magnitude and direction of the inferred acceleration, determined by fitting orbital models that include non-gravitational force parameters to the astrometric data, show patterns inconsistent with standard outgassing models. The acceleration vector does not consistently point radially away from the Sun as simple symmetric outgassing would produce. Instead, substantial, transverse, and normal components appear with magnitudes reaching 50 to 70% of the radial component, far exceeding the 10 to 20% level typical for normal comets. The direction of the transverse component varies in time without clear correlation to changes in solar distance or rotation phase, behaviors that standard outgassing models struggle to reproduce. Detailed modeling efforts attempted to explain the acceleration through complex outgassing patterns involving multiple discrete active regions positioned at specific locations on the nucleus and activating according to particular schedules as they rotate into and out of sunlight. By introducing sufficient free parameters including vent locations, orientations, activity levels, and time variable strengths, modelers can in principle fit any observed acceleration profile. This approach has successfully explained non-gravitational accelerations for many solar system comets, where ground truth validation came from spacecraft imaging that confirmed the postulated active region distributions. For 3I Atlas, achieving acceptable fits to the acceleration data requires active region configurations that directly conflict with the observed jet structures visible in high-resolution images. The jets point in specific directions determined unambiguously by their appearance in images from multiple viewing geometries. The thrust direction inferred from orbital dynamics points in different directions that would require different jet orientations. Additionally, the strength of outgassing inferred from spectroscopic measurements of gas production rates does not match the thrust levels needed to produce the measured orbital perturbations. The gas production falls short by factors of 3 to 5 in providing sufficient momentum flux to explain the accelerations. The most significant and difficult to explain component appears in the transverse acceleration perpendicular to both the sunline and the comet's velocity vector. Natural outgassing produces primarily radial accelerations with smaller tangential components arising from rotation effects and thermal lag. Transverse components perpendicular to the orbital velocity arise only through very specific geometric configurations, where active regions point sideways relative to the motion direction and maintain this orientation despite rotation. For 3I Atlas, the transverse acceleration persists at substantial levels across weeks of observation, requiring either continuous fine-tuned asymmetry that somehow maintains itself despite rotation, or forces completely unrelated to solar-driven outgassing that happen to point in directions unconnected to obvious physical drivers. Activity patterns uncorrelated with solar distance. The fundamental driver of cometary activity is solar heating, which increases systematically as a comet approaches the Sun and decreases systematically as it recedes following perihelion. This relationship between solar distance and activity level is among the most basic and well-established principles in cometary science, observed across hundreds of objects spanning centuries of recorded observations. The activity typically follows a power law where brightness and gas production rates scale with solar distance raised to some negative exponent, with typical values between -2 and -4. This means activity increases by factors of 4 to 16 for each halving of solar distance, a strong and easily measured effect. For 3I, ATLAS, light curve monitoring, and spectroscopic observations conducted over several months spanning inbound approach, perihelion, and outbound departure tracked the comet's brightness and gas production rates with sufficient cadence to reveal deviations from this fundamental pattern. Instead of the expected smooth monotonic increase toward perihelion followed by symmetric decline, the data shows irregular variations superimposed on the general trend that do not correlate with solar distance. Outburst events occurred at times when solar heating was actually decreasing as the comet receded from perihelion. Activity levels fluctuated on timescales of days, with amplitude variations reaching factors of 2 to 3, far exceeding the smooth changes expected from the gradually varying solar distance. Attempts to correlate the activity variations with the nucleus rotation phase met with mixed and ultimately unsuccessful results. For some activity variations, particularly those with periods close to the measured rotation period, correlations appear, suggesting that localized active regions rotating into and out of direct sunlight drive the brightness changes. This is normal behavior for comets and explains many of the shorter period variations observed. However, the largest and most dramatic outbursts show no correlation with rotation phase, occurring at different rotational orientations across multiple spin cycles. These phase-independent outbursts cannot be explained by fixed surface features like discrete vents or ice patches that would show regular periodic behavior tied to the spin. Solar-wind interactions provide another potential mechanism for driving activity variations independent of solar distance. Changes in solar wind pressure, density, or magnetic field strength might modify the efficiency of gas escape from the nucleus or trigger sudden releases of trapped volatiles through electrical or magnetic stress. Detailed comparison of activity variations with solar wind measurements from multiple monitoring spacecraft showed no consistent correlations. Individual outburst events sometimes occurred near times of solar wind pressure increases or interplanetary shock passages, but statistical analysis across all events found no systematic relationship. The probability of apparent correlations occurring by chance alone exceeded 30%, far below the threshold for claiming physical causation. The activity pattern anomaly implies either substantial internal energy sources driving outgassing, independent of solar heating, or control mechanisms that modulate surface activity according to processes unrelated to simple thermal response. For natural comets, the only significant internal energy beyond solar heating comes from radioactive decay and residual formation heat. Radioactive decay produces power outputs that vary on timescales of millions to billions of years, far too slow to explain day-to-day activity variations. Formation heat dissipates on timescales of thousands to millions of years for objects of cometary size, again much too slow. Chemical reactions between reactive species could provide rapid energy release on appropriate timescales. Various chemical systems store energy in molecular bonds that releases when reactions proceed, ranging from simple oxidation reactions to complex organic chemistry. However, sustaining repetitive outbursts over weeks requires either enormous reserves of reactants that would dominate the nucleus composition or extremely efficient triggering mechanisms that initiate reactions with precise timing. Laboratory studies of chemical reactions in ices under conditions relevant to cometary environments show that while reactions can produce transient heating events, the energy release rates and repeatability required to match observations far exceed what natural chemistry provides without artificial initiation or control. The dust-to-gas ratio reversal. In every comet studied in detail previously, gas production dominates over dust production in terms of mass flux from the nucleus. Typical dust-to-gas ratios by mass range from 0.1 to 1, meaning that for every kilogram of dust ejected, somewhere between 1 and 10 kilograms of gas sublimate and escape. This gas-dominated mass loss reflects the fundamental composition and structure of cometary nuclei, where volatile ices comprise the majority of the material and dust particles, represent rocky and carbonaceous inclusions embedded within the ice matrix. The gas provides both the energy through sublimation and the mechanical force through expansion that lifts dust from the surface and accelerates it away from the nucleus. 3I Atlas displays a dust-to-gas ratio measured at values between 3 and 5, depending on the specific observation date and measurement technique, representing a complete reversal of the normal pattern. For every kilogram of gas detected through spectroscopic measurements, 3 to 5 kilograms of dust appears in scattered light and thermal emission observations. This represents not a marginal deviation toward the high end of the normal range, but a fundamental inversion that has no precedent in comprehensive surveys of cometary dust-to-gas ratios spanning decades of observations. Measuring dust-to-gas ratios requires combining observations across multiple wavelengths and techniques, each sensitive to different components of the comet's mass loss. Spectroscopy in ultraviolet, visible, and infrared wavelengths quantifies gas production through analysis of molecular emission lines. The intensity of these lines relates directly to the number of molecules present and their excitation state. Careful modelling of excitation processes accounting for solar fluorescence and collisional effects converts measured intensities to gas production rates, with uncertainties typically around 30%. Dust measurements come from analysis of scattered sunlight in visible wavelengths, which depends on the total cross-sectional area of dust grains, and thermal emission in infrared wavelengths, which depends on dust temperature and emissivity. Combining these measurements with models of dust optical properties allows estimation of total dust mass production rates. For 3I Atlas, multiple independent teams performed these measurements using data from different facilities and different analysis techniques. The results consistently show dust production exceeding gas production by factors of 3 to 5. This represents a robust result confirmed across multiple observation epochs, spanning weeks of time and multiple viewing geometries. Cross-checks using different gas tracers and different dust measurement methods confirm the inversion. This is not a measurement artifact from any single technique or a transient phenomenon during one observation, but a persistent property of the comet's mass loss throughout the entire period it remained observable. Explaining dust-dominated mass loss requires either an extremely dry nucleus with minimal ice content or physical mechanisms that preferentially eject dust compared to gas beyond what normal entrainment processes provide. The measured water abundance, already established at just 4% of the coma mass compared to 50 to 80% for typical comets, places the nucleus composition far toward the dry extreme of any known population. Reducing volatile content further to explain even higher dust-to-gas ratios creates severe problems for understanding how the object formed as a coherent body and how it maintains structural integrity. Ice acts as the cement binding cometary nuclei together. Laboratory experiments and theoretical models both show that without sufficient ice content, dust grains cannot aggregate into stable bodies. The weak forces between dust grains, including van der Waals interactions and electrostatic attraction, provide insufficient binding strength to prevent disruption from tidal forces, collisions, or internal stress. Observations of asteroid families and collisional fragments demonstrate that purely rocky bodies without ice quickly break apart into rubble piles held together primarily by self-gravity. For a body with the estimated size of 3I Atlas, self-gravity alone cannot provide sufficient binding force to maintain integrity without ice providing additional cohesion. The coma asymmetry that rotates wrong. Cometary comas typically display some degree of spatial asymmetry in brightness, with enhancements in particular directions corresponding to active regions on the rotating nucleus surface. As the nucleus completes its rotation, these brightness patterns rotate with it, maintaining fixed positions relative to surface features. The rotation of coma asymmetry patterns allows mapping of where on the nucleus active vents or ice-rich regions are located. This technique has been applied successfully to many comets, providing information about surface heterogeneity that complements spacecraft imaging when available. High-cadence imaging of 3I Atlas captured coma structure with time resolution sufficient to follow brightness variations through multiple complete rotation cycles of the nucleus. Analysis of these image sequences reveals brightness enhancements and asymmetry features that rotate at rates inconsistent with the photometrically determined nuclear rotation period. Some coma features rotate faster than the nucleus spins, completing full rotations in 12 to 14 hours compared to the 16-hour nuclear period. Other features rotate more slowly or even retrograde, appearing to move backward relative to the nuclear spin direction. These anomalous rotation rates are not constant, but vary with time as different features appear, persist for hours to days, then fade. The pattern defies explanation through standard gas dynamics or dust fountain effects. Perhaps complex interactions between multiple gas jets create regions of enhanced density in the inner coma, where different outflow patterns collide and gas piles up temporarily. Detailed numerical simulations of colliding gas jets show that such structures can form but dissipate within minutes to hours as the gas continues expanding outward. The simulations predict that any density enhancements should remain stationary in the frame rotating with the nucleus, not rotate independently at different rates. The gas, velocities and pressures in cometary comas are too low to support organized vortex structures that might rotate independently through fluid dynamic processes analogous to atmospheric cyclones. Magnetic fields, organizing ionized gas and charged dust into structures with their own dynamics, provides a theoretical mechanism for creating independently rotating features. Interterrestrial magnetospheres and solar wind interactions with magnetized planets, plasma structures do exhibit rotation rates different from the underlying solid body. However, achieving these effects requires magnetic field strengths measured in nanoteslas at minimum, typically tens to hundreds of nanoteslas for robust organization. The magnetic field measurements around 3I Atlas, while anomalously high compared to normal comets, remain below 1 nanotesla in the coma regions where the independently rotating brightness features appear. Even invoking the highest measured field values and most favorable geometries, magnetic forces remain orders of magnitude too weak to overcome gas pressure and organize plasma into rotating structures. The rotating coma features persisted across multiple observing sessions, separated by days to weeks, ruling out transient phenomena like discrete outburst clouds or fragment halos that might show complex motion for brief periods before dispersing. The features maintained structural coherence, appeared as organized enhancements rather than random fluctuations, and displayed systematic rotation that varied smoothly rather than erratically. Something actively maintains these structures against the natural tendency for gas expansion and dissipation, and something drives their rotation at rates decoupled from the nuclear spin. Natural cometary processes, identified through decades of study, provide no mechanism capable of producing these behaviors. Nuclear condensations without fragmentation. High-resolution imaging of cometary comas occasionally reveals compact bright regions distinct from the central nucleus, features that astronomers call nuclear condensations. These bright spots, embedded within the broader diffuse coma, typically represent one of two phenomena: either concentrated dust clouds ejected during localized outburst events, or recently separated fragments produced when the nucleus splits apart under thermal or tidal stress. The distinguishing characteristic between these possibilities comes from tracking how the condensations move and evolve over time. Dust clouds expand and dissipate within hours as gas drag disperses the particles. Fragments follow ballistic trajectories determined by their separation velocity and the weak gravity field, drifting steadily away from the parent nucleus and eventually forming independent dust tails as solar radiation pressure acts on their individual comas. For 3I, Atlas, high-resolution images obtained during the perihelion passage revealed multiple distinct nuclear condensations, appearing as compact, bright regions with spatial scales of hundreds to thousands of kilometers, substantially smaller than the main coma, but much larger than the estimated nucleus size. Advanced image processing techniques designed to enhance faint structures and separate overlapping features identified at least 3, possibly as many as 5, distinct condensations present simultaneously during peak activity periods. Each appeared as a brightness enhancement, with a profile sharper and more concentrated than the diffuse background coma, but noticeably extended compared to stellar point sources in the same images. Confirming these features represented real structures at the comet's distance rather than foreground stars or cosmic rays striking the detector. The condensations displayed motion relative to each other and to the main nucleus that defied straightforward interpretation within either the dust cloud or fragment hypothesis frameworks. If these features represented separated fragments, their relative velocities measured from position changes across multiple images fell in the range of tens to hundreds of meters per second. For objects separated by the observed distances of thousands to tens of thousands of kilometers, these velocities correspond to separation events occurring hours to days before the observations. Fragment separation during cometary breakup events produces debris clouds following trajectories determined by the ejection velocity vector and subsequent gravitational and radiation pressure forces. Standard orbital mechanics, applied to the observed positions and velocities, predicts that fragments should rapidly drift apart, with separation distances increasing linearly with time for ballistic motion or following more complex but calculable trajectories if radiation pressure significantly affects the motion. The smallest fragments, those most affected by radiation pressure, should visibly accelerate away from the nucleus in directions roughly anti-sunward, producing elongated trails within hours. Larger fragments that are less affected by radiation pressure should follow nearly Keplerian orbits around the Sun that slowly diverge from the parent nucleus trajectory, creating angular separations that grow steadily with time. Neither predicted behavior matched what the observations showed, The nuclear condensations maintained loose spatial association with the main nucleus across observation periods spanning multiple days, neither rapidly dispersing like ballistic fragments, nor maintaining fixed positions like stationary coma structures. Their relative positions changed, demonstrating real motion rather than rotation of stationary features, but the motion patterns did not follow ballistic trajectories. Some condensations appeared to approach the main nucleus rather than recede, behavior impossible for ballistically ejected fragments unless gravitational capture occurred, which requires implausibly low separation velocities for the observed distances. Most puzzling, the condensations eventually faded from visibility without producing the debris trails that fragmentation events invariably create. When cometary nuclei split, each fragment becomes a miniature comet in its own right, surrounded by its own dust and gas coma, and trailing its own tail of material swept back by solar radiation pressure. These fragment tails remain visible for weeks to months after separation, providing unmistakable signatures of breakup events in long-term monitoring data. Famous examples include the spectacular multiple tails of Comet West and the string of pearls appearance of Comet Shoemaker-Levy 9. No such fragment tails appeared in continued monitoring of 3I Atlas as the condensations disappeared. Alternative explanations invoking transient dust clouds face equally severe difficulties in explaining the observations. Localized outbursts from discrete vents can indeed produce concentrated dust clouds that appear as brightness enhancements in images. However, detailed modeling of dust cloud evolution under realistic cometary conditions shows that such features dissipate rapidly as the gas expanding from the source region carries dust outward and disperses it into the surrounding coma. The timescale for a compact dust cloud to spread and merge indistinguishably with the background coma depends on the initial gas velocity, dust particle sizes, and the spatial scale of the feature, but typically ranges from hours to, at most, a couple of days for the conditions at 3I Atlas. The observed nuclear condensations persisted substantially longer than these natural dissipation timescales, remaining visible as distinct features for periods of 3 to 7 days, depending on the specific condensation tract. This extended lifetime requires either continuous dust production, maintaining the concentration against dispersal, or some mechanism actively confining the dust against natural expansion. Continuous production from a localized source would require sustained outburst activity at levels that should produce detectable gas emission from the source region. Spectroscopic observations showed no localized emission enhancements corresponding to the condensation positions, arguing against ongoing outbursts as the explanation. Physical confinement mechanisms that might prevent dust cloud dispersal include magnetic fields acting on charged grains or electrostatic forces in dusty plasma. Both mechanisms have been proposed in various astrophysical contexts and observed in laboratory experiments. However, the field strengths and charge densities required to provide confinement forces exceeding gas pressure and preventing expansion far exceed what measurements indicate exists in the 3I Atlas coma. Even the anomalously high magnetic fields detected, while puzzling in their own right, remain orders of magnitude below the levels needed for dust confinement. Electrostatic forces between charged grains can produce weak aggregation effects, but cannot overcome the strong outward gas drag in an actively outgassing coma. Some researchers tentatively suggested that the condensations might represent separate objects travelling alongside the main nucleus on similar heliocentric orbits, perhaps companions that formed together in the same parent molecular cloud, or objects ejected from the same source region that arrived at the solar system on nearly identical trajectories. This scenario requires extraordinary geometric coincidence for multiple objects to approach Earth's observing position with separations of thousands of kilometers while traveling at interstellar velocities of tens of kilometers per second. The probability calculations for such coincidences become vanishingly small when the full three-dimensional geometry and velocity space are considered. Additionally, if the condensations represented independent interstellar travelers, they should remain visible indefinitely, their apparent positions changing according to their individual orbits as both they and Earth moved. Instead, the condensations faded and disappeared from view over periods of days to weeks, suggesting either their destruction through some unknown process or their merger with the main nucleus through mechanisms that standard gravitational dynamics cannot explain for the observed separations and velocities. The nuclear condensations join the growing catalogue of features that resist comfortable classification within conventional cometary phenomena, pointing toward either completely novel natural processes operating under extreme conditions or artificial structures exhibiting controlled behavior. The ionization state problem. The gas in cometary comas exists in a dynamic state, constantly shifting between neutral molecules and ionized plasma through competing processes of ionization and recombination. Solar ultraviolet radiation provides the primary ionization source, with photons energetic enough to strip electrons from atoms and molecules, producing ions and free electrons. The solar wind contributes additional ionization through direct collisions between high-energy solar wind particles and cometary neutrals, and through charge exchange reactions where solar wind ions steal electrons from neutral cometary molecules. Recombination processes work in the opposite direction, with free electrons captured by ions reforming neutral species and releasing the ionization energy as photons. The balance between these competing processes establishes an equilibrium ionization state that depends on multiple factors, including the intensity of solar ultraviolet radiation, the density of the gas where higher densities promote recombination, the composition of the gas, since different species have different ionization and recombination rates, and the distance from the Sun, which affects both radiation intensity and solar wind properties. Decades of cometary observations combined with detailed plasma physics modeling have established expected ionization levels for various conditions, allowing astronomers to predict what fraction of cometary gas should be ionized at different distances from the nucleus and different solar distances. Spectroscopic measurements of emission line ratios provide direct observational constraints on the ionization state of cometary comas. Different ionization stages of the same element produce emission lines at different wavelengths, and the relative intensities of these lines encode information about how much material exists in each ionization state. Additionally, the properties of the emission lines themselves, including their widths and shapes, provide information about electron temperatures and densities in the emitting plasma. For 3I Atlas, comprehensive spectroscopic observations obtained with high-resolution spectrographs on multiple facilities reveal ionization levels that substantially exceed equilibrium predictions based on standard photoionization and solar wind models. The measurements indicate electron temperatures elevated to values 20 to 30% above typical cometary plasma temperatures measured under similar conditions of solar distance and activity level. While this may seem like a modest increase, plasma processes are extremely sensitive to temperature, with ionization rates depending exponentially on the electron energy distribution. The elevated temperatures imply ionization rates enhanced by factors of 2 to 3 compared to normal conditions. Even more striking, the spectroscopic line ratios indicate densities of highly ionized species like doubly ionized carbon and triply ionized nitrogen, at levels that standard photoionization models underpredict by factors of 10 to 20. Cross-checks using completely independent spectroscopic features confirm the ionization anomaly and rule out systematic errors in the analysis. Different emission lines probe different spatial regions of the coma and different ionization processes. The fact that multiple independent diagnostic ratios all indicate enhanced ionization levels provides strong evidence that the effect is real rather than an artifact of measurement errors or modeling assumptions. The anomaly persists across multiple observation epochs, separated by days to weeks. Demonstrating this represents a sustained property of the comet's plasma environment rather than a transient phenomenon occurring only during brief periods. Attempting to explain the enhanced ionization through increased solar ultraviolet radiation encounters immediate contradictions with solar monitoring data. Multiple spacecraft continuously observe the Sun across all wavelengths, providing comprehensive real-time measurements of solar output, including the ultraviolet bands most important for ionization. During the period when 3I, Atlas, passed through perihelion and the enhanced ionization was measured, solar activity remained within normal ranges with no unusual flares or sustained increases in ultraviolet emission. The measured solar irradiance at the relevant wavelengths was entirely typical for the phase of the solar cycle, providing no basis for enhanced photoionization rates. Solar wind variations offer another potential mechanism for enhanced ionization if the comet encounters regions of unusually dense or energetic solar wind during the observation period. Solar wind monitoring spacecraft positioned at the first Lagrange point between Earth and Sun measure solar wind properties continuously, providing detailed records of density, velocity, temperature, and magnetic field strength. Comparison of these measurements with the timing of enhanced ionization observations on 3I, Atlas, shows no systematic correlation. While individual measurements occasionally occurred during periods of elevated solar wind density or speed, statistical analysis across all observations found that enhanced ionization appeared equally often during quiet solar wind conditions as during disturbed periods. The correlation probability fell well within the range expected from random chance, ruling out solar wind variations as the systematic driver of the ionization anomaly. Electron impact ionization provides an alternative mechanism that could enhance ionization levels if populations of electrons with unusually high energies exist within the coma. In natural cometary plasmas, photoionization creates a population of thermal electrons with energies of a few electron volts, characteristic of the temperature established through energy balance between various heating and cooling processes. Some electrons gain higher energies through acceleration in electric fields associated with plasma instabilities and wave-particle interactions. These suprathermal electrons, while comprising only a small fraction of the total electron population, can contribute disproportionately to ionization rates, because ionization cross-sections increase with electron energy. Calculations of the suprathermal electron population required to explain the observed ionization levels through electron impact ionization show that approximately 10 to 20% of electrons would need energies exceeding 50 electron volts, far above the few electron volt thermal energies. Natural plasma processes in cometary environments do produce some population of energetic electrons, but comprehensive plasma simulations, constrained by spacecraft measurements at other comets, predict suprathermal fractions below 1% under conditions similar to 3I, Atlas. Achieving the 10 to 20% levels needed requires electron acceleration mechanisms far more efficient than standard wave-particle interactions or potential drops associated with typical plasma instabilities. Magnetic reconnection events, where magnetic field lines break and reconnect in different configurations, releasing stored magnetic energy as kinetic energy of charged particles, can accelerate electrons to high energies with substantial efficiency. This process occurs naturally in Earth's magnetosphere, in solar flares, and has been invoked to explain energetic particles in various astrophysical plasmas. However, efficient magnetic reconnection requires specific conditions, including magnetic field strengths of at least several nanoteslas and field geometries with oppositely directed field lines brought into close proximity. The magnetic field measurements around 3I, Atlas, while anomalously strong compared to typical comets, remain marginally at the threshold where reconnection becomes possible and show no clear evidence for the characteristic current sheet structures where reconnection occurs most efficiently. Plasma physics models exploring various mechanisms for enhanced ionization, including combinations of suprathermal electrons, energetic neutral atoms producing cascade ionization, and exotic processes like shock acceleration or plasma instabilities, consistently fail to match observations without introducing artificial energy sources or invoking plasma parameters well outside the ranges that measurements constrain. The ionization state problem represents yet another aspect of the 3I Atlas plasma environment that challenges natural explanations, requiring either undiscovered acceleration mechanisms operating with unprecedented efficiency or external energy sources driving the plasma into states that passive solar heating and wind interactions alone cannot achieve. The synchronized jet activation pattern. Cometary jets form when localized regions of the nuclear surface become active, with solar heating driving sublimation of near-surface ice and gas escaping through vents or porous surface layers carrying entrained dust along with it. Different regions activate at different times as the rotating nucleus carries them into sunlight, creating temporal patterns of brightness, variations that reflect the distribution and properties of active areas. For typical comets, this produces light curves showing periodic variations with the rotation period, often with multiple peaks per rotation if several discrete active regions exist at different longitudes, and with peak amplitudes and timings that shift gradually as the solar illumination geometry changes throughout the orbit. High cadence monitoring of 3I, Atlas, through multiple complete rotation cycles revealed jet activation patterns that deviate significantly from these standard expectations in ways that suggest coordinated rather than independent behavior. Instead of jets activating sequentially as different surface regions rotate into sunlight in a pattern determined solely by the rotation geometry and solar illumination angle, the observations show multiple jets turning on and off in apparent synchronization, despite being located at different positions on the nucleus that receive peak illumination at different times. The synchronization persists across many rotation cycles, ruling out coincidence as an explanation, and requiring some mechanism that coordinates activity across spatially separated regions. Detailed analysis of image sequences with time resolution of minutes to hours tracked the brightness variations of individual jets, identified by their distinct orientations and positions relative to the nucleus. For a nucleus rotating with a period of 16 hours, surface features separated by 90 degrees in longitude receive peak solar illumination 4 hours apart. If jet activation followed purely local thermal response to solar heating, jets from these locations should show brightness peaks offset by 4 hours, creating a light curve with multiple peaks distributed throughout the rotation period. Instead, the observations showed jets from different locations brightening and fading together within time windows of less than 1 hour, far shorter than the 4-hour offset that geometric considerations predict. Standard explanations for synchronized activity in comets invoke subsurface connections between active regions with interconnected pore spaces or fracture networks, allowing pressure communication that triggers simultaneous outbursts when gas pressure exceeds structural strength anywhere in the connected network. This mechanism has been proposed to explain correlated activity in some solar system comets and is physically plausible for bodies with complex internal structure. However, achieving the degree of synchronization observed requires essentially instantaneous pressure communication across spatial scales of kilometers, the estimated nucleus size, which in turn requires gas flow velocities through the porous medium approaching or exceeding the local sound speed. Laboratory measurements of gas permeability in various ice and ice dust mixtures under conditions relevant to cometary nuclei show that realistic porous materials have permeabilities that limit gas flow to velocities far below sound speed, even under substantial pressure gradients. Pressure pulses propagate through porous media at speeds determined by the permeability and compressibility, typically orders of magnitude slower than the sound speed in the gas itself. For a 5-kilometer nucleus with realistic permeability values, pressure equalization between opposite sides of the nucleus requires timescales of hours to days, far too slow to explain synchronization within 1-hour windows. Achieving the observed synchronization through subsurface pressure communication would require permeabilities exceeding measured values by factors of hundreds to thousands, implying internal structure more like empty cavities with minimal solid material than realistic cometary aggregate. Magnetic field effects coupling different regions of an ionized coma could potentially coordinate activity if electrical currents flowing through plasma created feedback loops that affected surface activity in multiple locations. This represents a more exotic mechanism, rarely invoked for cometary activity, but theoretically possible if strong enough fields and sufficient plasma density exist. The measured magnetic fields around 3I, Atlas, while anomalously high, remain below the threshold where direct magnetic pressure on gas would significantly affect sublimation rates. Electric fields associated with plasma currents might affect dust, grain charging and lofting, potentially coordinating dust emission even if gas sublimation remains controlled by local thermal conditions. Testing this hypothesis requires detailed measurements of electric and magnetic field configurations, synchronized with jet brightness monitoring, observations that exceed what was obtained during the 3I Atlas apparition with available instrumentation. However, theoretical estimates of the field strengths and current densities required to produce observable effects on dust emission exceed the measured values by significant margins, making this natural explanation unlikely even without detailed confirmatory observations. The mechanism also struggles to explain why synchronization appears so precise and repeatable, rather than showing the variations and fluctuations that would characterize a system driven by turbulent plasma processes. The most striking aspect of the synchronized activation pattern appears in observations spanning multiple consecutive rotation periods. If the synchronization arose from some transient condition or unusual but natural confluence of factors, it should appear intermittently with periods of normal, unsynchronized behavior interspersed. Instead, the synchronization persisted with remarkable consistency across all high-cadence observation sessions, totaling more than 100 hours of monitoring. Every rotation showed the same pattern of multiple jets brightening together despite their different orientations and positions. This repeatability across many cycles argues against random coincidence or transient phenomena and requires some stable mechanism maintaining coordination. Some analysts noted that the synchronization pattern, combined with other anomalies in the jet geometry and orientation, resembles what might be expected from artificial control systems maintaining desired thrust vectoring or surface activity patterns. While this interpretation remains speculative and controversial, the observation that conventional natural mechanisms fail to produce such precise and persistent coordination across spatially separated regions adds another item to the list of behaviors that challenge standard cometary physics frameworks. Whether natural or artificial in origin, the synchronized jet activation demonstrates phenomena beyond what current models of cometary activity predict or explain: spectral line width anomalies. The width of spectral emission lines from cometary gases encodes information about the velocity distribution of the emitting molecules through the Doppler effect. Molecules moving toward the observer produce emissions slightly shifted to shorter wavelengths, while molecules moving away shift to longer wavelengths. When integrated over the entire population of molecules with various velocity components along the line of sight, this produces a spectral line with finite width determined by the velocity distribution. For cometary comae, the dominant contribution to line widths comes from the expansion velocity of gas flowing outward from the nucleus, with additional smaller contributions from thermal motion of molecules at the kinetic temperature and from any turbulent velocity fields present in the expanding gas. High-resolution spectroscopy of 3I Atlas emission lines reveals line widths that vary systematically with distance from the nucleus in ways inconsistent with standard gas expansion models. Close to the nucleus, where gas acceleration is still ongoing as sublimating molecules escape the surface and interact with previously emitted material, the observations show line widths narrower than expected for the measured outflow velocities. Farther from the nucleus, where the gas should have reached terminal velocity and expansion should be primarily radial with little variation in speed, the line widths are broader than standard models predict, implying either higher velocities than spectroscopic measurements indicate, or non-thermal velocity dispersions from turbulence or other processes. Standard gas dynamic models for cometary comae, validated through decades of observations and spacecraft measurements at multiple comets, predict specific relationships between line width and distance from the nucleus based on the acceleration profile of expanding gas. Near the surface, molecules have low velocities as they just begin escaping, producing narrow lines. As gas expands and accelerates through conversion of thermal energy and potential energy to bulk kinetic energy, velocities increase and lines broaden. At distances beyond a few tens of nucleus radii, the gas reaches terminal velocity determined by the energy budget, and line widths should stabilize at values corresponding to this velocity plus thermal contributions. For 3I Atlas, spectroscopic observations obtained with spatial resolution sufficient to measure line profiles at different projected distances from the nucleus show the opposite pattern in the inner coma. The narrowest lines appear at intermediate distances rather than closest to the nucleus, and line widths actually decrease slightly, moving outward from the innermost measurable regions before increasing again at larger distances. This non-monotonic behavior cannot be explained through standard expansion models, regardless of what parameters for gas temperature, composition, or source distribution are assumed. The narrow lines at intermediate distances require lower velocity dispersion than exists closer to the nucleus, implying gas somehow becomes more organized with more uniform velocity as it expands. Contrary to expectations from entropy increase during free expansion. In the outer coma, the line widths exceed predictions by amounts that cannot be explained through temperature variations alone. Converting the observed line widths to velocity dispersions accounting for thermal motion and instrumental resolution yields values 20 to 40% higher than the terminal velocities measured through other techniques, including Doppler shift analysis and proper motion of coma structures. This implies either systematic errors affecting all the other velocity measurements, considered unlikely given multiple independent techniques, all producing consistent results, or additional velocity dispersion from non-thermal sources adding to the Doppler broadening. Turbulence in the expanding gas could provide additional velocity dispersion beyond the bulk expansion velocity. Turbulent flows contain velocity fluctuations on a range of spatial scales, from large eddies to small viscous dissipation scales that would add random velocity components contributing to line broadening. However, generating significant turbulence in the low-density expanding cometary coma presents challenges. Turbulence requires energy input to offset viscous dissipation, and in the coma environment, potential energy sources include instabilities at interfaces between different gas streams or between gas and dust. Detailed hydrodynamic simulations of cometary gas expansion show that while some level of turbulence does develop, particularly where multiple jets interact, the velocity dispersions generated remain small compared to the bulk expansion speed, typically a few percent of the terminal velocity, rather than the 20 to 40% excess widths observed. Alternative explanations explored included systematic variations in outflow velocity across the source surface that would produce velocity gradients imprinted on the expanding gas, or time-variable source strengths that would create shells of gas with different expansion speeds overlapping along the line of sight. Both mechanisms can produce line broadening beyond what steady uniform expansion would generate. However, matching the observed radial profile of line widths requires extremely specific source distributions, or time variations that seem contrived rather than natural consequences of surface activity patterns. Some researchers noted similarities between the observed line width patterns and what might result from external forcing, accelerating or decelerating gas parcels after they leave the surface, potentially through electromagnetic forces acting on ionized components or through collisions with high-energy particles. While speculative, this interpretation at least provides a conceptual framework that could produce the non-monotonic line width profile. Natural mechanisms providing such external forcing remain to be identified, with all proposed candidates facing quantitative difficulties when detailed calculations are performed using measured field strengths and plasma densities. The missing hydroxyl radical cloud. When water molecules in cometary comae absorb solar ultraviolet photons, a fraction undergo photodissociation, breaking apart into hydrogen atoms and hydroxyl radicals rather than being ionized. The hydroxyl radical, consisting of one oxygen and one hydrogen atom, is chemically reactive but stable enough to survive for hours in the low-density cometary environment before photodissociating further into atomic oxygen and hydrogen or reacting with other species. Hydroxyl produces strong emission lines in the ultraviolet, particularly a cluster of lines near 308 nanometers wavelength, making it easily detectable and one of the most commonly observed species in cometary comae. The spatial distribution of hydroxyl around comets follows predictable patterns determined by the photodissociation rates, the expansion velocity of the parent water molecules, and the finite lifetime of hydroxyl before it dissociates further. This creates an extended cloud of hydroxyl emission, typically many tens of thousands of kilometers across, substantially larger than the water cloud itself, because hydroxyl survives long enough to travel farther from the nucleus before being destroyed. The hydroxyl cloud has been detected and mapped around every water-rich comet observed with sufficient sensitivity in ultraviolet wavelengths, providing a reliable tracer of water activity. Ultraviolet spectroscopic observations of 3I, Atlas, specifically targeting the hydroxyl emission lines, reveal emission intensities far below what the measured water production rate predicts. The water production rate derived from direct water emission lines in infrared wavelengths and from hydrogen, Lyman alpha emission indicates gas production levels that should generate hydroxyl emission easily detectable by the instruments used. Instead, the hydroxyl lines appear at barely detectable levels, requiring extensive integration time and careful background subtraction to confirm their presence at all, and even then showing intensities 10 to 30 times weaker than expected. The deficit cannot be explained through uncertainties in water measurements alone. The water production rates are constrained by multiple independent techniques, including direct detection of water emission, measurement of hydrogen emission produced by water photodissociation, and estimation from overall activity levels and coma brightness. While individual measurements carry uncertainties of 30 to 50%, the convergence of multiple methods provides robust constraints that cannot be adjusted by the factors of 10 to 30 needed to explain the hydroxyl deficit. Additionally, the temporal variations in water production rates inferred from different tracers correlate with each other, confirming they measure the same underlying process rather than representing unrelated systematic errors. Several potential mechanisms could suppress hydroxyl emission relative to water, even if the actual water abundance remains high. If the water photodissociation produces hydroxyl predominantly in excited vibrational states that quickly dissociate further before radiating in the observed ultraviolet lines, the emission could be suppressed. However, laboratory measurements and theoretical quantum chemistry calculations of water photodissociation determine what fraction of hydroxyl forms in which vibrational states under solar radiation conditions, and these studies predict that observable ground state hydroxyl should be produced at levels inconsistent with the weak emission observed. Alternatively, if some process rapidly destroys hydroxyl through chemical reactions much faster than photodissociation normally removes it, the population could be depleted before it emits detected photons. This requires reactions between hydroxyl and other coma species at rates far exceeding what gas kinetics calculations predict for the measured coma densities and compositions. No plausible reaction pathway has been identified that could remove hydroxyl at the required rates without also producing detectable products or requiring abundances of reactant species far beyond what observations show. The hydroxyl deficit becomes even more puzzling when combined with the water deficit discussed in earlier sections. The coma shows both less water than typical comets and less hydroxyl than the limited water present should produce. This double suppression requires either that water photodissociation follows completely different pathways from standard solar system comets, producing different products through unknown chemistry, or that the water measurements themselves are systematically misinterpreted. Attempts to construct self-consistent models that explain both the low water abundance and the hydroxyl deficit within natural frameworks have so far failed to produce satisfactory solutions that match all observations simultaneously. The anomalous heliocentric light curve. Cometary brightness as a function of solar distance follows well-established patterns that allow prediction of how bright a comet will become as it approaches the Sun and how quickly it will fade as it recedes. The relationship is typically expressed as a power law where brightness varies with some power of the inverse distance to the Sun, with exponents typically ranging from 2 to 4 for most comets. An exponent of 2 corresponds to a comet, where brightness changes purely due to changing illumination geometry, while larger exponents indicate that intrinsic activity increases with decreasing solar distance. The specific exponent measured for a comet provides information about how sensitive its activity is to solar heating and has been correlated with composition and physical properties. For 3I, ATLAS, comprehensive photometric monitoring spanning the entire observable apparition from discovery through post-perihelion fade-out, provides a detailed heliocentric light curve that deviates significantly from standard patterns. The brightening phase during approach to perihelion followed a power law relationship, but with an exponent substantially lower than typical, measuring between 1.5 and 2 compared to the 3 to 4 typical for active comets. This indicates that intrinsic activity increased more slowly with decreasing solar distance than normal, suggesting either unusual composition with volatiles that respond less strongly to heating, or some process buffering the response to changing solar input. More striking anomalies appear in the post-perihelion light curve. After passing perihelion, comets typically fade following a power law with an exponent similar to the pre-perihelion brightening, creating roughly symmetric curves when plotted versus solar distance. Asymmetries do occur, particularly if the comet undergoes fragmentation or major outbursts, but absent such discrete events, the inbound and outbound portions of the light curve should match within observational uncertainties. For 3I, ATLAS, the post-perihelion fading followed a power law with exponent, significantly steeper than the pre-perihelion brightening, approximately 2.5 to 3 compared to the 1.5 to 2 measured inbound. This asymmetry indicates that the comet faded faster relative to solar distance on the outbound leg than it brightened on the inbound leg, behavior opposite to what seasonal effects typically produce. Some comets show brighter outbound light curves than inbound due to seasonal differences in which hemisphere receives most illumination, analogous to terrestrial seasonal lag, where autumn can be warmer than spring at the same solar distance due to thermal inertia in oceans and ground. For 3I, ATLAS, the sense of asymmetry goes the opposite direction, with faster than expected fading implying either rapid depletion of surface volatiles or abrupt decrease in active surface area after perihelion. Attempts to explain the light curve asymmetry through progressive deactivation of surface area as sublimation removes surface ices and leaves behind desiccated crusts face quantitative challenges. The timescale for developing inhibiting crusts depends on the depth of volatile ice, the porosity and thickness of overlying dust layers, and the efficiency of volatile transport through the developing crust. Detailed thermal models incorporating these processes predict that mantle formation occurs gradually over many orbital passages for short-period comets or over extended periods near perihelion for long-period comets. The rapid transition from slow pre-perihelion brightening to steep post-perihelion fading observed for 3I, ATLAS, occurs over timescales of days to weeks, far too short for natural crustal evolution. Discrete events, like partial fragmentation or major outbursts, could cause abrupt changes in light curve slopes if they significantly altered the active surface area or exposed fresh volatiles. However, as discussed in earlier sections, no evidence for fragmentation appears in any monitoring data, and while outbursts did occur, their frequency and magnitude do not show systematic changes around perihelion that would explain the light curve asymmetry. The outbursts appear throughout both inbound and outbound portions, with similar characteristics, ruling them out as the cause of the asymmetric brightness evolution. The heliocentric light curve anomaly adds to the growing list of activity patterns that deviate from natural cometary behavior. The specific combination of shallow pre-perihelion slope, steep post-perihelion slope, and lack of correlating structural changes is unprecedented in comprehensive surveys of cometary light curves. While individual comets occasionally show unusual brightness evolution due to specific circumstances, the pattern displayed by 3I Atlas does not match any previously documented case and resists explanation through conventional activity models, even when allowing generous freedom in parameter choices. The plasma tail disconnection failure. Cometary plasma tails, composed of ionized gas molecules swept back by the solar wind, occasionally undergo dramatic disconnection events where the entire visible tail detaches from the comet and drifts away downstream, while a new tail reforms at the nucleus. These disconnection events occur when the comet crosses sector boundaries in the interplanetary magnetic field, regions where the field direction reverses as the Sun's rotating magnetic field creates a spiral pattern in the solar wind. The field reversal creates conditions where magnetic reconnection can occur, severing the magnetic field lines that thread through the plasma tail and causing the tail to pinch off and separate. Disconnection events have been observed and studied in detail for many comets, with observations correlating well with spacecraft measurements of sector boundary crossings and theoretical models of magnetic reconnection in cometary plasmas. The events follow predictable patterns, including characteristic timescales for the disconnection to develop, visible kinking and twisting of the tail as magnetic stress builds before breakage, and reformation of a new tail from the nucleus over subsequent hours to days. The physics is well understood and represents one of the clearest examples of solar wind interactions directly shaping visible cometary structures. Solar wind monitoring data indicated that 3I Atlas crossed at least 3, possibly 4, sector boundaries during its perihelion passage, based on magnetic field direction reversals detected by spacecraft at the first Lagrange point. The specific crossing times could be calculated with reasonable precision, accounting for the solar wind travel time from the monitoring point to the comet's position. Imaging campaigns were organized to observe the comet during predicted crossing times to capture expected disconnection events, providing opportunities to study these phenomena in an interstellar visitor for the first time. The observations showed no disconnection events during any of the predicted crossings. The plasma tail, visible in images sensitive to ion emission, maintained continuous structure throughout periods when it should have separated and reformed according to standard magnetohydrodynamic models. Careful analysis of image sequences spanning the crossing windows confirmed the absence of the characteristic kinking, twisting, and detachment signatures that accompany disconnections. The tail showed normal variations in brightness and width, responding to changes in solar wind pressure and the comet's gas production rate, but maintained continuous connection to the nucleus without disruption. Several potential explanations were explored to understand why 3I Atlas failed to display disconnections despite apparently crossing sector boundaries. Perhaps the plasma tail was too faint or too narrow for the disconnection signatures to be visible with the available image resolution and sensitivity. Analysis of detection limits and comparison with tail brightness showed this explanation unlikely, as the tail was clearly visible and brighter than tails in which disconnections have been successfully observed in previous comets. Perhaps the sector boundary crossings predicted by first Lagrange point measurements did not actually occur at the comet's location due to spatial variations in the interplanetary field structure. This explanation fails because sector boundaries are large-scale structures that maintain coherence across spatial scales much larger than the distance between the monitoring point and the comet. More exotic explanations invoke unusual plasma properties or magnetic field configurations that somehow prevented reconnection despite field reversals. If the plasma density in the tail was much higher than typical, increasing the plasma pressure relative to magnetic pressure, reconnection could be suppressed. However, the plasma densities inferred from emission line intensities fall within normal ranges for cometary tails. If the comet possessed an intrinsic magnetic field strong enough to dominate over the interplanetary field in the tail region, it might prevent reconnection by maintaining connected field line topology. The magnetic field measurements discussed in earlier sections show fields enhanced above normal cometary values, but still far too weak to dominate over the interplanetary field at the distances where plasma tails extend. The failure of plasma tail disconnection despite multiple sector boundary crossings represents another case where 3I Atlas behavior deviates from well-established patterns observed in hundreds of comets. The physics of sector boundary interactions and magnetic reconnection in cometary plasmas is among the best validated through combined observations and theoretical modeling. Finding a natural explanation for why these processes failed to produce expected visible effects in this one case, while operating normally in all other observed comets, challenges the principle that physics operates uniformly across different objects in similar environments. The deuterium to hydrogen ratio. The ratio of deuterium to hydrogen in cometary water provides crucial information about formation conditions and origin, because this ratio varies significantly across different solar system reservoirs and reflects the temperature and irradiation history of the material. Deuterium, the heavy isotope of hydrogen with one proton and one neutron, forms in the Big Bang and is destroyed in stellar interiors, creating cosmic abundance patterns. Additionally, chemical reactions at low temperatures preferentially incorporate deuterium into molecules compared to normal hydrogen through kinetic isotope effects, enriching cold interstellar ices in deuterium relative to the cosmic ratio. Measurements of deuterium to hydrogen ratios in solar system comets have revealed values ranging from about 1 to 3 times the Earth-ocean ratio, with Oort cloud comets generally showing higher ratios than Jupiter family comets and variations correlating with formation location in the protoplanetary disk. These measurements provide tests of solar system formation models and chemical evolution. For 3I Atlas, representing material formed in another stellar system, the deuterium ratio offers a rare opportunity to compare compositions across different planetary systems and test whether isotopic patterns are universal or vary with the stellar environment. High-resolution infrared spectroscopy, specifically targeting water emission lines that allow discrimination between normal water and deuterated water, revealed a deuterium to hydrogen ratio in the 3I Atlas coma that significantly exceeds any solar system comet previously measured. The ratio measures approximately 4 to 6 times the Earth-ocean value, depending on analysis, details, and assumptions about excitation conditions, placing it well above the range observed in the most deuterium-enriched solar system objects. The measurement is robust against systematic errors because deuterium produces spectral lines at wavelengths distinctly separated from normal hydrogen lines, allowing unambiguous identification without interference or blending concerns. The elevated deuterium ratio implies formation in an environment with very low temperatures and/or with high ionization rates that promote deuterium enrichment through ion molecule chemistry. Interstellar clouds with temperatures of 10 to 20 Kelvin and high cosmic ray ionization rates, produce ices enriched in deuterium through well-understood chemical pathways. Material incorporated into comets without significant thermal processing preserves these high deuterium ratios. However, temperatures in protoplanetary disks generally exceed the cold interstellar values, causing some deuterium depletion through equilibration reactions at higher temperatures. Matching the observed deuterium ratio requires either formation in an unusually cold protoplanetary disk region, temperatures below 30 Kelvin compared to the 50 to 100 Kelvin typical for comet-forming regions in solar system models, or formation directly from cold interstellar material that never thermally equilibrated in the protoplanetary disk. The first scenario requires specific disk conditions that may occur in disks around low-mass stars or in the outer regions of more massive disks. The second scenario requires incorporation of pristine interstellar material without thermal processing, possible if the comet formed very rapidly before disk temperatures rose, or if it represents material from the edge of the protoplanetary disk that remained cold. Alternatively, the high deuterium ratio might indicate formation around a different type of star, with different deuterium abundance in its natal molecular cloud. Galactic chemical evolution models predict that deuterium abundance varies somewhat with location in the galaxy, and with the metallicity of the stellar environment due to the balance between Big Bang production and stellar destruction. However, these variations are modest, typically 20% or less, insufficient to explain deuterium ratios elevated by factors of 2 to 3 relative to solar system comets. Achieving the observed ratios through starting composition alone would require formation from material with primordial Big Bang composition that never cycled through stellar interiors, possible only in extremely metal-poor environments, unlike typical star-forming regions. The deuterium measurements on 3I, Atlas, while providing fascinating glimpses into potentially different formation conditions than solar system comets experienced, also raise puzzles when combined with other compositional anomalies. The very low water abundance, extreme nickel to iron ratio, and unidentified spectral features suggest a formation environment with chemistry fundamentally different from standard protoplanetary disk models. Whether all these anomalies can be explained through a single consistent formation scenario in an exotic but natural environment, or whether they indicate material processed through artificial means, remains an open question that the deuterium ratio adds complexity to rather than resolving.